Hi everyone, and once again, a big thank you for being here today. It's a Friday evening, and I couldn't think of a better way to spend my Friday evening than to be here. So, thanks for being here with me. Um, Today, we are touching upon a very interesting topic which is very close to my heart: function safety system for semiconductors. And I think some of you were in the last presentation as well, webinar. But for those who weren't, here's a quick about me section. So I'm like Vinayak mentioned before, I'm the founder of Prakriti Energy and Technologies. I have a master's from Decibels in Automotive Electronics, and I worked as a safety researcher across many industries, aerospace, drones, Robert Bosch as autonomous driving, and at ST Microelectronics in the field of automotive semiconductors. And so working in these places has really helped improve my perspective on how safety works across various tiers of automotive and how everyone approaches safety differently. So I believe that I would like to share my experiences with you today. All right. So in the last presentation, the ones who were there, you remember that we were touching upon HARA, the Hazard and ASIL Risk Assessment. And I did not delve into too many details. And I did get some feedback from you guys that you wanted some more real examples. So here I am talking of a very complex example. In fact, I think that's going to be the theme of this webinar. The examples that I'll be taking are going to be pretty complex. And that's so that you can appreciate how safety works. It's very easy to use, simplistic examples to get the point across, but I believe that I'd like to challenge you guys as well on how systems operate. So I want to begin with so by the way, we'll be beginning with the HARA, and then later on we'll talk about how safety works, especially for hardware. We'll get there. But yeah, I want to begin with the HARA for regen braking. I'm sure all of you already know what regen braking is, but for those who don't, regen braking is a specific feature of electric vehicles in which the vehicle decelerates by a preset amount of brake torque the moment the driver elevates the foot of the accelerator pedal. Now, of course, the example I'm going to take here is kind of fictitious, but it is as close to the real world as possible. So it's possible that some vehicles operate in a different fashion, but I think for the sake of example, this is good enough. So I'm thinking of an example of an EV where the regen braking operates the moment the driver takes the foot off the pedal. As usual, there are about 3 or 4 levels. Level 0 meaning no regen braking, and then 3 levels of braking with the increasing harshness of braking. So level 1 braking could be something like 0.2 G or 0.3 G, which means essentially 3 meters per second square or 4 meters per second square. Level 2 could be 4 to 5, and level 3 could be 5 to 6 meters per second square of deceleration. All of this is natural, with meaning that the driver is not expected to press the brake pedal. And this happens automatically. This is a special feature of EVs. And so it's natural to talk about the art of one pedal driving, which means that because essentially both the acceleration and the deceleration are happening by controlling the accelerator pedal, we call it one pedal driving because it's very unlikely that in most cases the driver would use the brake pedal at all. So it's called one pedal driving. And an assumption that I want to make beforehand, because it's a very obvious assumption, the regen braking depends on the powertrain, which is the motors in case of EVs. And so I assume that it does not affect the performance of the hydraulic braking anyway. So it's called a mechanical override. If the electrical systems fail, the driver could always, push through and get the brake torque. And another somewhat less important assumption being made here is that the intensity of regenerative braking is independent of vehicle speed. Now, of course, I know that in the real world, the OEMs try to make it speed variant, but for the sake of the example, I'm taking it in. And because all of us were there last time, I mean, but for those who weren't, we have 3 parameters on the basis of which we estimate the risk for any given feature. And so if you are if you're a driver who drives an EV on a regular basis, you kind of expect regen braking to be there. I mean, you expect it as much as a driver in a normal car expects the brakes to work. So as you drive EVs more often, you end up depending on regenerative braking a lot. I do that. And so if a regen braking is not working, that's a pretty serious use case, because in that case, it's essentially like very low brake torque. And so given the hazard of missing regen braking, we estimate the three parameters of severity, exposure, and controllability. Briefly explaining them, severity means that in case that failure happens, which is that the regen braking is not working, how likely would the severity of an accident be? Exposure meaning that how likely are you going to be in a scenario where a missing regen is dangerous? And finally, what can the driver do to prevent the accident from happening in case of missing regen? And to make this very interactive, I want to directly jump away to a poll. So Vinayak. Right, thank you. So guys, I want to ask you here, what do you think is the severity rating of a missing regenerative regen braking? The thing is on your screens, and please vote in. At the same time, please also vote for the controllability rating. What can the driver really do? So as a reminder, severity means if the missing regen happens, how dangerous would the accident be? And if can the driver really do something to avoid that accident? I'm going to wait 25 seconds more. Okay, so let me share my screen so that everyone can see the answers. So for the severity rating, it's very, very interesting that we have ranges of answers across S0 to S3. Would someone who voted for S0 explain the rationale? So 8 people voted for S0. Can one of you explain your rationale? Vinay, can they unmute and talk, or you have to raise their hands?
Yeah, I can give them the permission. Would you like to give in to them?
So someone wants to talk about S0? Or S3?
Yes, you can unmute and talk.
Yeah, hello everyone.
Hello.
Yeah, since the vehicle is decelerating during this region, means the speed is less than the desired speed, and there is no harm to the driver. That's why I have selected yes zero.
No, actually the case was the regen braking is missing. So the driver expects there to be a brake because they took their foot off the pedal, but the braking did not happen. You know what I mean?
Yeah.
So, okay. And anyone who voted for S3, you want to talk about your answer? Okay. What about controllability? If anyone who voted for C0 can talk about their rationale, or C3, the extreme ones. I know it's Friday evening, but I'd love to hear some answers here, just so that I know you're with me.
Hello, sir. Good evening.
Hello.
Yeah, for C0, why we have given it? Because the driver could able to still control the vehicle using the mechanical brakes.
Right. I agree with you. Anyone for C3 who they voted? So C3 means that there is no controllability whatsoever. Would anyone like to defend C3? Okay. I see no answers. So, first of all, HARA is subjective to the location, subjective to the style of driving in a specific location or country, subjective to many other reasons. So the rationale that I'll be providing depends on what I assume in case of certain driving conditions. Of course, it's possible that you might interpret those conditions differently, and so your answers might look different. But here's my rationale, and of course, we can argue about it later. All right, so the way I see it, I see SIS3 because the fact that region braking is not there is loss of brake torque. And if it does not initiate, we are missing almost 6 meters per second square of brake torque, with the assumption that this region braking can kick in to that levels. So level 3 region braking. So imagine you being at high speed, expecting a braking because someone in the front slowed down the vehicle and the vehicle did not slow down. So the way this situation is interpreted, it will lead to a potentially catastrophic situation of collision speeds of about 50 kph. And so I would like to give it a rating of S3. On the topic of exposure, I think it's pretty straightforward. That's why I did not even put it in the poll. For a regular EV, region braking is a daily scenario. Everyone uses region braking every day, all the time. And so if it was missing, it might be dangerous in any of those occasions. And controllability, I almost agree with you, Dinesh, I think, who answered. But what I'd like to say there is that your assumption is correct that a missing brake torque should be identified by an intended driver, who will then apply the main brakes and go on. But from a purely realistic standpoint and a conservative standpoint, the fact that EVs are getting a lot more common, and assuming a day that all cars are EVs and everyone's driving just an EV using region braking all the time, it is possible that people, when they get more confident on the region braking, they sometimes even forget to use brakes. And when I say forget, I mean it takes a bit longer for them to even remember that they can put the main brakes on. I'm not saying this is C2 or C3, which means it's very, very uncontrollable, but it's at least C1 in my opinion. Again, I speak of this from my own experience because when driving an EV, I feel that even I forget sometimes that I have main brakes. And so I take a second longer to apply the main brakes. So that's why I give it a rating of C0. And so 3 plus 4 plus 1, 8, which means an ASIL rating of B. So we derive a safety goal to say that the system must avoid a missing brake torque due to faulty region braking unit at an ASIL B. Again, I'm keeping it a bit simple. I'm not going into the zones of FTTI and safety criteria and so on. Simply saying that in this interpretation, the ASIL is considered to be ASIL B. Any questions or any disagreements? I'm happy to engage on this. All right, assuming there are none, moving on. Now, given the fact that we're talking about the region braking system, let's talk about types of faults. Now, again, I'm skipping sections here. It's a short webinar, so I'm not going to be very exhaustive. But given that the region braking has a certain safety goal attached to it now with a certain ASL, I want to talk about the faults that can be impacting it. And the categories of those faults, let's begin from the item/system. In this case, region braking. 3 categories are considered here: hardware, software, and mechanical. So a system might makes up of usually 3 entities, 2 of which fall in the zone of ISO 26262. And so hardware, software, and mechanical is outside the scope of ISO. And hardware is susceptible to systematic faults and random faults. Software is susceptible to systematic faults. Yes, and now I use the terminology systematic faults and random faults. What exactly are those? Systematic faults. Hello.
Sorry, Priyank, you can go ahead.
Okay. Systematic faults are reproducible, which means that they happen with given certain conditions. And so if you reproduce those conditions, you reproduce the fault. They're generally due to a flaw in design, manufacturing, etc. Here, remember that we're talking of both hardware and software. So design faults, manufacturing faults can happen in both hardware and software. They're predictable and correctable. So you can actually predict the rates of, not just the rates, but even why they happen, and you can correct them even during design phase. And generally speaking, systematic faults are traceable to a human error during the design phase. Again, this could be a lot more complicated depending on the kind of software we're talking about. If we go into the area of machine learning or AI, then this might not always be true. But essentially speaking, this is what defines a systematic fault. On the other hand, the random faults are of three various properties. They are irreproducible, which means you cannot reproduce them. They happen due to a random/chance event. And even if you repeat those conditions, it's not necessary that the fault will happen again. You cannot fully eliminate random faults. And this is where the ISO definition of unreasonable risk comes in. You can never achieve zero. Perfect safety does not exist. You just need to take it to a level where it's adequately meeting certain given standards. And this is a very important thing to remember, that random faults cannot completely be eliminated. You can design systems to mitigate against them, that they don't become dangerous. And that is the entire point of hardware safety. And finally, they're traceable to natural causes, which means that they can happen due to naturally occurring events, which humans have no control over. We can reduce the danger that they pose, but we cannot fully eliminate. I know this was a lot, so I would like to stop for some questions here, if there are any. If it's questions on this slide or this slide, I'm happy to take some. I see a question in the chat by Anaga Himadri. Can you explain how you concluded the safety goal to be ASIL-B? Anaga, are you there? Yeah, so perhaps you can unmute yourself and we can speak about this slide, because this is how I concluded to be ASIL-B. If you're asking that, how does this combination of it lead to, just take a sum of S3, E4, C1, so 3 plus 4 plus 1. It's a lazy way of coming up with ASIL, but there are charts which we can also see later on. But essentially, if the sum is 7, it's ASIL A. If it's 8, it's B. If it's 9, it's C. And if it's 10, it's D.
So is this according to any standard that we are following? Yeah.
I cannot hear you. Can you be a bit louder?
The sum of this is 7, and that's why you mentioned it will be ASIL-B, right? So
The
can you
sum
just
is the sum is 8. 4 plus 3 is 7 plus.
yeah, correct. Can you just elaborate on how do you consider it as ASIL-B?
Can you repeat the last part of your question?
Like how did you come to a conclusion as to how it is ASIL-B is my question. Is there any standard that we are following?
Yes, we are following ISO 26262.
2662, okay.
Yeah, and SEC, the numbers along with them, 3, 4, 1. If you sum them and it's 8, that corresponds to ASIL-B or ASIL-beta. And if it's 7, so for example, if it's C0, it would be ASIL-A. And so on and
Can
so
you
on.
just tell me in which chapter this is documented?
I think it's part 3 or part 4, one of those.
Okay, yeah. Thanks.
Yeah. Any other questions, anyone, on this slide, perhaps? Okay, no questions, I assume. I want to take 2 minutes to introduce you guys to something I've been planning for many years. and I finally get to execute it. I'd like to formally inaugurate a 3-day program called Functional Safety Systems to Semiconductors. It would be a very, very exhaustive program, face-to-face in Bangalore next month. And there, the concepts that I'm touching upon here will be extended in great detail. I'm very thankful to Decibels Lab for collaborating with me on this. And in this program, we'll be touching upon various topics. So it's a 3-day program, like I said, the day one talking about various kinds of analyses across various industries as well, automotive, aviation, industrial, and medical. Day two would talk about what it takes to build resilient hardware and resilient software, and how to validate that using certain analysis. Day two was going to be talking about redundancy, partitioning, voting mechanisms, integrity management, and so on. And finally, on day three is going to be an extremely detailed and advanced level analysis of FMEDAs, DFAs, FTAs in hardware domain, in semiconductor domain, in software domain. And the day three would be really suitable for you if you're interested in how these analyses exactly work in the greatest possible details. Directly coming from ASIL to 6262 and the best practices I have learned across various industries. There's going to be a certification, and if you fall in these categories of either an architect or an engineer or a cybersecurity professional or in marketing and sales team in automotive companies, you should attend this. The pricing and so on, you can have a look at later on. And if there is certain expectation that you have from this program, you can always DM me to make it more suitable for you. It's going to be in Bangalore, 13, 14, and 15 December. And I welcome you guys to attend it. Thank you very much. Coming back to the presentation. So again, I'm skipping chapters, and I'm going to talk about how to build the hardware for the system that we just discussed. So for example, if you are a supplier working on the region braking system, if you refer to part 5 of ISO 2262, you see these targets, and it's sort of very overwhelming, and I want to talk about them a bit more in detail. So if you're building an ASIL beta system, you need to achieve a 90% SPFM, which means single point fault metric. And for ASIL D systems, which some of you might have worked on, for example, braking systems or steering systems, the coverage expected is as high as 99%. And for latent fault metrics, the numbers go from 60 to 90%. But what exactly are these numbers? Let's begin with a single point fault metric. The ISO shows a very complex formula. This is not the most complex formula out there, but the estimation for SPFM is by this formula. What do these numbers mean? So lambda stands for failure rate, and lambda SPF stands for single point fault, which means that a single point fault is a fault in one of those components that may directly lead to an unsafe system behavior, in this case, the region system. And lambda SPF means the failure rate, or what is the probability of occurrence of those faults, which can directly lead to unsafe system behavior. On the other hand, residual faults are those faults which are single point faults, and for which you implemented a safety mechanism to mitigate against those faults, but nothing is perfect, and nor are the safety mechanisms. And there's always going to be a very, very small proportion of faults that will leak through, and that leakage is essentially called a residual faults. And that's the definition of lambda SPF and lambda RF. The denominator here, lambda, is the total failure rate. And this is the sum of all kinds of failure rates, the ones which are SPF, which are RF, which are multi-point faults, safe faults, so on and so on. And if you essentially think about it, SPFM is nothing but a representation of the coverage of the faults of your system. So remember, we're talking about random hardware fault matrix, which is in the scope of part 5. So if you're building a hardware for region breaking systems, you need to achieve a coverage of 90% for ASIL B for SPFM. And the SPFM is a proportion of the faults covered by the safety mechanisms. This is the SPFM. Similarly, LFM is called latent fault matrix, and it is calculated using this formula, wherein MPF MPF is multi-point faults, and DP means detected/perceived, which means these are the failure rates which are associated with a hardware element which is perceived or detected multiple point faults. Detected or perceived means that due to some safety mechanisms, the driver is able to detect and can control against those faults. So those faults never really become dangerous. And latent faults are those faults which remain hidden. So as per the English definition of the word latent/hidden, what it means is that those faults which remain hidden in the system, okay, and they only manifest themselves or become dangerous when something else also fails across the system. And I know you'd like to see some examples on what this really means, but are there any questions? I'm happy to repeat it if you'd like.
Hello, sir. I have a question.
Mm-hmm.
From where you get those equation? Maybe you can suggest me some book where, if I want to learn more about it.
Sure. It's the part 5 of ISO 26262.
Okay, noted. Thank you.
Yeah.
Hi, sir. Can you explain this SPFM again?
Yeah.
Yeah. So what I understand is, if it is the probability in which you can save a failure, a metric which can prevent the failure. Is it like that?
No. So first of all, let's go back to basics. These are random faults. You
Right.
cannot control them. They will happen for sure. So given the fact that they will happen, what is the likelihood that you have a safety mechanism deployed that will detect it?
Okay.
So it's, let's say, again, I have a very good example later on, but simplistically speaking, let's say there are 100 failures.
Mm-hmm.
For those 100 failures, how many are not covered at all by any safety mechanism? And even the ones which are covered by safety mechanisms, what is the leakage? And then the leakage plus the failures which have no mechanism at all, they help us calculate the single point fault filter. Let me please hold the question until the end. There's an example which I hope you'll understand, help you understand.
Yeah.
And let's come back to this later on. Ashok, for the comment that essentially, so your question is that mostly Siemens standard is used, and can you use MIL standard? ISO does not mandate any thing here, so it suggests some standards. In my experience, I have not seen MIL standard being used, 217. The reason why I think, and I have not used it, so I'm saying this, that aerospace environments are very harsh compared to automotive. The vibration levels are very high, the temperature fluctuations are too high, the pressure changes are very high, and you might have to start with a lot worse baseline compared to an automotive use case. So that's my assumption for military standard not being used, but I don't think ISO necessarily says you cannot use it. It's a state-of-the-art handbook and you can use it. It's like that. But I would suggest against using it because you'll start from a very, very poor, very worse or conservative baseline, and you might not be able to achieve the automotive grade in that case. But I do not have a study to prove it, so it's an open question for me as well. Ashok, does that answer your question? You're there.
Yes. Thank you. Yeah.
Thank you. So any other questions on this, guys? SPF, LFM, I know it's complicated. And let's get a bit more into it. And I'm going to do another poll now. I want to do another poll just to see what you currently understand from the words SPF and LFM. So Vinayak, please. You're going to see some questions on your screen. And there are 3 questions. Again, I want to repeat, there are no right or wrong answers. It's our interpretation of how we see it. Having said that, there are some engineering parameters which always stay there. So give it your best shot. All right. So the winner for the first question is stray radioactive particles in packaging material. The second most voted answer was cosmic particles impact. I'm glad to share these were the 2 right answers. These both are great examples of random faults. Because if you think about it, all the other faults, over voltage, incorrect software design, EMI-MC noise, you can both trace back to a human, and you can also lead to a flaw in design. I mean, if you think about it, incorrect software design is a great example of a flaw that a human had while in the code itself. But cosmic particles impact and your packaging material will have certain radiation levels, which you cannot fully eliminate because, as you all learned in class 11th, everything around us is radioactive. It's just that intensity is lesser. So perfect answers right there for question 1. For question 2, dependent failures, actually, the answer is completely the opposite. So the winner here is dependent failures. The point here being that dependent failures are the worst impacted by homogeneous redundancy. Okay, so what does homogeneous redundancy mean? It means that having parallel systems to do the same thing, but they having an identical design. Imagine you have a device and or a sensor, let's say, and you want to capture the data more reliably. So you tend to use another sensor of the exactly same kind. What will happen with that is that both sensors, because they are the exactly same kind, if there is a failure somewhere, systematic failure, for example, that systematic failure will reach both those sensors. And so they're negatively impacted by homogeneous redundancy. Same as safety decomposition. Safety decomposition means breaking down your safety goals and expecting that redundant systems take over. But the expectation is that the systems are heterogeneously redundant. The winner here is supposed to be random hardware fault matrix, which means that if you have systems which are fully duplicated, it is very unlikely that the same cosmic particle or any cosmic particles will hit the same 2 components exactly at the same point. Cosmic particles slash stray radioactivity. Now, of course, I'm not saying that this is enough, but at least from a purely minimalistic standpoint, the hardware random fault matrix take advantage from the fact that you have a homogeneous redundancy. And which analysis is most appropriate to connect system FUSA requirements with the semiconductor design? In my opinion, it's FTA, fault tree analysis. I say that because fault tree analysis is is the quantitative analysis, and it helps you to take a top level safety goal. So in this case, for example, if you go back to regen braking example, we were expected to achieve 90% single point fault metric. Similarly, there are stringent requirements for the total failure rate as well, which is called PMHF. And it helps you to take a top level safety goal at vehicle level, which is calculated at OEM level, and permeate those requirements to tier 1 and tier 2 and tier 3 and tier 4 suppliers as well. And that's what an FTA helps to achieve. This FTA can be done at OEM level, tier 1 level, tier 2 level, depending on the specific product. All right, so very interesting answers, everyone. Thank you very much. Now, let us take a working example, which I think is the most awaited part of the presentation. We started with the example of missing region breakdown. Please do focus on this because this is a bit complex, and so it will help if you hear as well what I'm saying. So we started with the topic of missing regenerative breakdown. Now, it's obvious that 2 major systems that work towards it are the braking unit and the motor unit. There are many more, I know, but again, keeping it simple for now. The braking unit essentially comprises of the pedal part, where the foot is on the accelerator pedal. For the moment, I'm assuming that to be a part of the braking unit because the input of that goes to the braking system first. And so it's a part of the braking unit. And motor unit. The motor unit is the actual electric motors that produce the brake torque. So both of them contribute towards making regen work. And if one of them fails in some way, this will lead to the top level violation of safety goal. Braking ECU. I repeat myself. The assumption was the accelerator pedal input goes to the braking ECU first. So the target or the safety goal for the braking ECU will be avoid transmitting erroneous brake pedal data. Sorry, I think I meant accelerator pedal data here to the motor unit. And the corresponding requirement for motor ECU will be that avoid incorrect circuit switching to ensure motor enters dynamic mode. What this means is that the braking ECU, let me correct that right away to avoid confusion later on. The brake ECU must process the pedal data correctly before it gives it to the motor unit. And the motor unit must make sure that it properly switches the motor from a motor mode toward generator mode to create electricity to store it in the batteries and reduce brake torque as a byproduct. Okay. I'm going to take the tree of the braking ECU a bit further. I'm going to take two examples here. The core is processing instructions incorrectly. The core meaning that braking ECU will have sort of a microcontroller device or a microprocessor, or depending on architecture, certain sort of an intelligent core which will be processing all the instructions, or the pedal sensor sending the data incorrectly. So the fault being inside the sensor itself. Even if the core is working properly, but the input it receives is garbage. All right. So this is a architecture of the fault, I assume. Now we have this architecture. We have a sensor microcontroller, we have a sensor transducer, and we have a watchdog that monitors the performance of the transducer at all times. Now let us explore this tree by sensor sending incorrect data to finally arrive at an mean in this case. Now, let's say the driver actually took the foot off the accelerator pedal, and the driver expects certain brake torque to be there. But the pedal is processing the data incorrectly, which means that even if the driver took the foot off the pedal does not transfer that data to anybody else, in this case, the code. So this will not initiate the regen braking at all. Now, the explanation here is that the failure in the sensor may lead to an incorrect pedal data being transmitted to braking ECU. I think that's straightforward. FM, failure mode 1. Now, the reason why the pedal data did not work correctly is because the transducer delayed operations. Again, not going into many details, but there is a transducer there which converts the actual position of the pedal and converts that into electrical signals, which are then forwarded to the core. So let's say there was a delay in the operation by the transducer. So at T0, the driver took the foot off the pedal, but until T whatever, till T1 second, T2 seconds, the information was not relayed to the core. So the system did not initiate the regen braking. That's a failure mode 1. In this case, it's a single point fault. And why I say that is because by this single failure alone, the failure mode 1 will lead to directly a pedal sensor sending incorrect data, which takes me back to this tree, and that will lead to missing regen brake torque. So this faulty operation of the transducer leads to a direct missing regen brake torque. And so it has the capability to lead to a single point fault. Now, given this data, let's say in my architecture itself, I add a watchdog. A watchdog, as we all know, it's a timing device which calculates if the certain unit is processing instructions within a certain time frame, and if it's not processing within a certain time frame, it sends an error output with a coverage of 50%. Now here the coverage of the DC means that The watchdog here is only able to detect 50% of the times when the system is delaying. Again, do not go into the physics and the mechanics of it, just focus on the data on the screen. And so in this case, because it is not able to detect 50% of the faults, the rest of the 50% becomes residual. I know this was a lot. So we took a failure mode. This was initially a single point fault. We added a monitor, and these faults became residual faults. The assumption here being that we considered only FM1. There could be many more failure modes for the sensor, but again, taking a smaller insight. Now, this we considered. But what about watchdog now? Because now watchdog is a part of the architecture and it can also incorrectly work. So the job of the watchdog is to monitor the transducer if it's not pinning at all. But if the watchdog itself fails, it is not an SPF. Because the failure of a watchdog will become critical only if the transducer also fails. But if the transducer did not fail in the first place, a watchdog failure will remain hidden. You won't even know it's there, right? So the safety mechanism, due to a failure, shut off itself. It's something like that. And assumption here being that I'm not monitoring the watchdog itself. So for example, you could think of monitoring the watchdog performance also, but I'm not assuming that, right? To make the example simple. So in this case, because none of the watchdog faults are being monitored, the latent fault matrix, actually I did not mean 100% LF, I meant 0% LF, which means that 100% of the faults remain undetected for the watchdog. %, LFM, you did not have any coverage at all for the safety mechanism, and so your LFM matrix goes back to 0. To prevent this, if you remember, for ASIL beta or ASIL B, we needed at least 60% LFM. So if you were to design the system, you will have to add a monitor for the watchdog itself. Now you can add that using a startup test or something else, a software routine, for example. It depends on the certain use case, but that's how SPF and LFM and residual faults come into calculation. And yeah, I'm happy to take questions because it is also the end of the session overall and time for Q&A. And I'm happy to repeat any section if you'd like to. Okay, I assume none. So thank you very much for being here. As a reminder, the 3-day program on functional safety systems semiconductors will be held from 13 to 15 December, face-to-face in Bangalore. I encourage you to register for it. And yeah, please feel free to DM me on LinkedIn or my email. I'll be happy to discuss, take questions, or tailor the program according to your specific needs. Thank you very much.